Video 3 of section 7.2, integration by parts. Notice again we're looking at the same formula here. We're going to use this formula all the way throughout, keeping in mind that u and dv are nothing more than placeholders, as well as u and v du. This is the example we're looking at this time. In the last example, you remembered we let u equal the algebraic, and my dv ended up being the exponential. Now again, I don't know how this might affect this particular problem, but we might want to consider the same thing, is that if I let u be the algebraic, that's going to simplify down when I take its derivative for du, and dv being the sine function, that doesn't make it any more complicated, but that sine function does just transfer over to a cosine function in some form or another. So what I'm going to do is I'm going to go ahead and remember that everything in here has to be part of my u dv. So I'm going to pick a u, I'm going to pick a dv. I'm going to pick those two in terms of relationship to the previous example. Now keep in mind, again, I'm going to let it be equal to something based on something I've already tried. If it worked before. Now, if it worked before, it doesn't mean it's going to work now. So letting u equal x could be a good starting point, but it doesn't have to work. If it doesn't work efficiently for us, then swap. Make sure your u is then sine of x, and my dv ends up being the x dx. So, but in this case, I'm going to go ahead and try and use the tried and true, the algebraic simplified down. The exponential didn't change at all. Well, the sine function shouldn't change at all. So, the derivative of u is going to be du is just 1 dx. And the integral of v, well, what is the integral of sine? Remember, if we've forgotten, there's a nice little unit circle trick that this is the cosine, this is the sine, this is the negative cosine, this is the negative sine, in that order. And the derivatives will always go this way, d dx. And your integrals will go backwards in this order. Okay, so in this case, with this, again, sine, derivative of sine is cosine, cosine goes to negative sine, and so on and so forth. So I know the integral of sine is negative cosine. So there's my negative cosine of x, and again, I don't need a dx for that piece. So if I do this correctly and I go ahead and use the formula, this thing right here is the integral of u dv. If this thing right here is the integral of u dv, that means that I need to have equals uv, and uv is x times the negative cosine. So I'm going to go ahead and write equals, and I'll put the negative up front just because I prefer the negative up front, x cosine of x. So that's my u and my v multiplied together from the formula right here. Don't forget the minus sign, the integral of, and then I have v du. So v is my negative cosine of x, and my du is nothing more than dx. And again, notice, by letting u equal x, dv equals sine of x, utilizing this formula, we end up with an integral that should be easily evaluatable. Keep in mind, this stuff right here doesn't change. That's the part that already came out of the integral. My next step is to recognize that the negative times the negative is a positive, and the integral of cosine, again, if you want, you can follow this rule right here, goes backwards to just sine. So this is nothing more than the negative x cosine of x. The integral of cosine is simple, and again, that's the intent, is that this secondary piece should always be simple, plus sine of x plus c. Don't forget to tack on that plus c. And that's the end of that problem. Again, once you've gotten it down to no more integrals, you're done. That's a very key statement. Once you have no more integrals left in your problem, you must tack on that plus c if there are no bounds, and you're done.